All right, so we are moving to the last part of the introduction to quantum thermodynamics, and I'll turn the lights off in a minute. What I wanted to emphasize is that by now you already have heard a lot of important information and suggestions that is relevant to doing practical QCD calculations. And one of the goals for this school is to teach you not just about theory, but also how do you put together the quite technical information about the QCD theory into a calculation that you can actually do, let's say, for the LHC, for the EIC, maybe Jefferson Lab. And that's what we are going to discuss in this last part of the introductory lectures. But let me now go back to the formula for factorization of hidden cross sections in the Canadian factorization formalism. And essentially, by now we know that for a large class of observables, which are infrared safe, we only need to know the perturbative part of the calculation. Now, for the other observables, we need to know the short distance hard cross section. Now, the hard cross section is what we call is an infrared part of the particle scattering cross section. It's basically the particle scattering cross section from which we removed collinear singularities and in which we count the source singularities. And so this cross section, the hard cross section, is denoted sigma by sigma hat. But then also we need to know the running coupling alpha S. If there are masses that are quarks that are not small compared to the hard scale, we need to include the masses of the quarks, so the masses also can run. And of course, we also need to include parting distribution functions. So the typical formula that you will get will look something like this. Now, again, the formula will kind of vary depending on the complexity of your observable, but you always need to have this one hard scale. Let's say in DS it will be Q that sets the typical values of the renormalization and factorization scale in the hard cross sections. Again, let's look how this works again very carefully. Suppose we look at the DS, which is kind of classical example of the observable that depends on one hard scale Q, which is much larger than 1 GV squared. Well, we wrote it as a combination of or convolution of the hard cross section sigma hat, and let's see what the hard cross section depends on. So it will depend on alpha S, which must be small. So therefore, mu R must be larger than 1 GV. And then it typically will depend on dimensionless quantities. And the way you can see that it will depend on dimensionless quantities up to some overall prefactor that is not so important here. Well, you can just do the dimensional analysis that Aurora was discussing in her lecture. And then you can show that the sigma hat really depends not just on Q squared or mu R squared or mu F squared on their own, but if it has a dimension 0 in units of momentum, so you must have Q squared over mu R squared and Q squared over mu F squared. So these are the only combinations. Of course, here again, I assume there is only one physical momentum scale that contributes, right? And okay, and now let's ask why we need to set mu R and mu F of order Q. Well, generally speaking, this the hard cross section will contain logarithms of any kind of dimensionless ratio, right? So it will contain log Q squared over mu R squared. It will contain log Q squared over mu F squared, and this can be raised to some arbitrary power depending on the specific type of the contribution. So therefore, if mu R or mu F are very different from Q, so these logs can become large, and so they will destabilize the convergence of perturbation theory. So therefore, we would like to set mu R very close to Q or mu F very close to Q, right? So how close? Well, that's our choice, and that's what I will discuss next, right? Because if we don't, then our perturbation theory for the hard cross section doesn't converge. Right, so that's why we select mu F and mu R to be of order hard scale, not be much smaller or much larger than typical hard scale. Now, of course, what this also means is that the PDF now depends on mu F. And so in mu F, you have other scales. You have lambda QCD, right, some kind of low perturbative scale. You also have masses of the quarks, masses of the light quarks in this case, UDS, which are very small. Okay, so therefore, F generally will contain very large logarithms of mu F squared over mq squared, like masses of the quantum field. But that's okay because this is an opportunity function. We just evaluate the whole order expression for f, and that's why we don't bother about these large logs because they are big. Okay, now so that's kind of the overall picture, right? So one message therefore, if you have one hard skill, well, you immediately know what the choices of the R and F should be. Well, now unfortunately, it's not always the case that you have one hard skill. So in the typical processes, you will have you also have so you will also have multiple scales. You have masses of the quark. So we talked about QT, the transverse momentum that can be very different from Q, and then factorizations becomes more challenging. Okay, so then now okay, so we'll get to this question of multiple scales towards the end of the lecture, but yeah. Okay, what I would like to discuss now quickly, okay, so what are the other issues related to the choice of the QCD scales? Well, let's take another example, which is, okay, in this case, it is a purely infrared safe observable, which is the ratio, the total cross-section for hydro production in the plus and minus collisions. And as we discussed already, so this cross-section, it is infrared safe, it doesn't contain any PDF or permutation function. Okay, so then if you calculated it up to order alpha s cube, so you get the following expression for the right-hand side. Okay, so basically it will depend on some function delta that is expanded in powers of alpha s, and you see there are some logarithmic terms of mu squared over q squared. Mu is equal to mu r here, right? So okay, so then you immediately say, okay, mu squared must be over q squared, but can we do better? Right, so what if we choose some prefactor in mu is equal to some constant times q? So will we get a better convergence? Okay, let's talk about it for a second. What are our options? So can we do better than mu equal to q? So now why we want to do that? Well, the reason we say, okay, based on this pattern of the logs, we will try to guess what is missing. We would try to guess the missing high order corrections. And maybe there is something in this pattern of these logs that tells us how this high order corrections behave, and maybe we will select the choice of meal that minimizes the missing high order correction. Okay, so then what would be your ideas? So how can we try to estimate the missing high order correction based on that? Is it possible? Let's try to brainstorm. So what okay, so do any ideas come to mind? Any ideas? Yeah, so you see what the problem is, right? So we see there are these logs, but we'd like to see if we can minimize this missing high order correction. So we try to get better convergence for this prediction. And that's actually what physicists will often do, right? So you do a calculation and then they do some magic, they try to find a scale that actually minimizes potentially the missing high order correction, and then there is a long debate that is happening about what is the right choice. Okay, so any suggestions? Anything you could imagine? For example, okay, so here we really have the series expansion, right? So can you guess about the missing high order term, missing term in the series expansion based on what you already have? Any thoughts?
You can have it's kind of similar tower of these logs and u squared, q squared. So I mean, u squared equals q squared should minimize down, and the alpha s cube suppression will get rid of that constant.
Right. Okay. Well. Okay. So now one thing obviously is that you can just set mu squared equal to q squared, and it will kill all the logs, right? But it doesn't do anything about the constant terms, right? So the constant terms won't really care about the logs, right? So that's one important message is that if you look here, well, okay, so you have the first order term is 1, then you have here 1.4092, then you have minus 12,805. And actually, this term, if there were no suppression by alpha s over pi, you get a much larger factor here, right? Now, you could imagine how these factors arise. Well, they arise because the high order additive contributions become more complicated, and you have simply the combinatorial growth
of possible contributions. So therefore, generally speaking, what you would expect that if you go to high orders, these coefficients can even grow. And so you have kind of, well, basically competition between the smallness of alpha S and the growth of these coefficients, okay? All right, so that's one thing. Now, then, okay, so the other thing you can do is that, let's say, okay, so like, if you try to understand estimate the high order term, missing high order corrections in the actual calculation, what would you typically do, given this information? Yes?
So, what I would do is I'll take the terms that are given on the RHS, and then I take a derivative with respect to mu. I already know how delta would run with mu from the top equation.
Okay.
And then the terms with the log terms, they can be directly differentiated. And I put those equal to 0. Like delta minus these terms and differentiate them, that is equal to 0, and then.
So basically you look for the minimal sensitivity of this
Yes.
with respect to mu.
Yes.
Okay, minimal sensitivity. Okay, so that's one way best. Very good. This is a very good idea, by the way, because many people thought about this, and so we'll see what happens. Other ideas. So how can we estimate the missing high correction? Even if we don't know what it is, but what can we do? Or what do people typically do with this information?
RG improve.
So RG improve, okay, so here we don't know how to RG improve. Yes, so we don't know how to improve it because it comes from the hard coefficients. We just don't know how to improve it, but in principle, there can be pi-squared terms that we can resample others. So that people do that. But also again, I give you the, okay, I give you a cross section and I say estimate the missing high of the correction. What do people often do with the scale? Anyone did a real calculation?
Scale variation.
They do scale variation, right? You say, okay, I can estimate my missing high of the correction by varying the scale mu up and down, right? Now, is it sufficient to estimate the high of the correction? Like, for example, doesn't say anything about this final terms. Right, so the missing high of the variation of the scale only tells us about the log terms. It does not tell us about the constant terms. Okay, very important. Now let's try actually. Okay, so try to compare both ideas. Actually, what's happening here, right? So that basically we take this expression. We know that the coefficients depend on mu. Alpha S depends on mu, but the exact delta to all others does not depend on mu. So therefore, the more terms we have, the less mu dependence we have. Okay, so that's one important thing why we do high and high order calculation, because we reduce dependence on mu with each order of the calculation. That's just by construction of the calculation. So that's why doing high order corrections are important, right? So then you ask, well, what scale should we choose, right? So it must be of order mu q. Different from q is not good. Okay, but what do we do if we only know these two terms after order alpha S squared? Okay, so then what we will do is that we will do some numerical analysis. Okay, and so here is an example how this expression behaves. So we take alpha S equal to close to the world average value. Q34 GeV, I think it's one of these fixed target experiments. Now, if we take 5 flavors of quarks, and here what I do, I plot delta versus mu, which is q times 2 to the power p. And I plot p on the horizontal axis. Okay, so delta 1 includes only one order of alpha S, delta 2 includes 2. Okay, so then we can apply the variation of the scale by a factor of 1 plus 2 of order 2, right? Okay, but before we do that, we need to select the central scale. And we can apply the principle of the minimal sensitivity. We look for the place where the derivative with respect to mu, in this case with respect to p, vanishes, right? So this will be our point right here. It kind of looks okay. Actually, delta 2 is close to delta 1, which is good. I think you can say, well, maybe the order should not change much when you go from the first to the second order. So this looks like a good scale somewhere here. So then we vary the scale up and down by a factor of 2. So, and this is our estimate for the missing, the yellow band is the estimate for the missing yellow high order correction. Okay, so then let's see what happens now if we calculate the true high order correction. Okay, so then what do you think? Did we capture the true high order correction? So who says yes?
But just make a bet. So now you have to make a bet that you've made a, okay, so like in real life, you need to make a bet that this is your correct estimate. Who thinks that we did not capture it? Okay, who is not sure? Okay, so most of us are skeptical, and because you think I'm setting you up, right, for something. And so, okay, and so the answer is okay. So now let's include delta 3 calculated exactly. It's actually, now you see that it's, okay, so it's the flattest curve of all of them because the scale dependence really cancels. But we focus on this region here, right? So see delta 3, okay, it's kind of close, but it's not really perfectly within the yellow band, right? So if we look at now at the estimate, well, the yellow band was close, delta 3 undershoots it, okay? All right, so then what do you think? Was our value and the error estimate about right? What was it, good estimate? Was it bad estimate? What are your thoughts?
Pretty good.
It was pretty good, right? So, but now if you place $1 million that it is good, well, clearly it's not, probably it's kind of not very good move, right? Because there is some mismatch and comes from several places that have nothing to do with the scale dependence. Okay, now this example, okay, so it's simple, but it shows also what happens in the actual calculation. Somebody will ask you, estimate the scale dependence and make a bet about the missing high order correction, but these things continue happening even with the N3 law calculation or whatever. Actually, we have examples in research showing that the people, again, spend lots of time arguing about these kind of issues. Okay, all right, now let's talk about the active pattern flavors. Okay, so what is the deal here? So it goes back to the question that was asked earlier. Okay, so in principle, we have 5 quarks. Now we know that 2 of them are very light. When we talk, okay, so basically the current masses for U and D quarks are just a few MeV. Strange is a little bit heavier, 200 MeV. And then charm and bottom are actually have very large masses. It's 1.3 and 4.5 GeV. Okay, so then an interesting question emerges, which is the following. Do we write the pattern distribution function for charm bottom quark? Okay, and this actually, now if you phrase it in the theoretical terms, you can phrase it in a different way. You say, do I apply the MS bar normalization scheme to regularize terms with charm and bottom propagators? Now, the other alternative is the on-shell scheme. And so how many of you know the distinction? How many of you have heard about the on-shell scheme and how different it is from the MS bar scheme? Okay, good. Not everyone. Okay, now, so what's the on-shell scheme? Well, the on-shell scheme is a kind of the oldest scheme. Okay, before I talk about the on-shell scheme, let me mention the following. So the heavy particles can come in to cross sections in 2 ways. Like, for example, we count how many pattern flavors are active in a given process. Well, they can appear in 2 ways. One way is that we have enough energy in the collider that we can explicitly produce these particles in the final state, like real long kind of propagating fields, right? And so then we have one type of active flavors that is set up by the square root of S, by total energy of the collisions. Here it's called NF in the final state. It's the maximal flavor of the quark that can be produced at a given square root of S. Okay, now then there is another contribution that comes from the loop diagrams. It comes from the loop diagrams, and those are not, they're just virtual quarks. They kind of come and go, right? And so the number of flavors in the loop diagrams is not fixed. You can determine, you can set it based on your renormalization scheme. So therefore, okay, obviously it can happen that the number of flavors in the loop is not the number of flavors in the final state. But also you can choose an F. For the same square root of S, you can use NF equals 3 in the loop or NF equals 4 in the loop. And what this means is that it means the following. So when we count, so basically when we say what we choose the NF, the number of active flavors, we select essentially the definition of alpha S, running masses, and the PDFs. What we say is that whenever we calculate the loop corrections, well, we have a choice. We put this loop correction into the hard cross section, or we can put a part of it, or maybe all of it into alpha S, so the running mass. And
and the choice of NF in the alpha S or running mass is determined, is basically set by this number NF of active flavors. So what this basically means is that we still, typically this works as following. So we look at the quarks with different masses, and suppose we have a scale mu. So then a typical scale scheme will tell you if the mass of the quark is smaller than the scale mu. So we assume that this quark is renormalized in the MS bar scheme. And so therefore alpha S and PDF will include a non-zero contribution from these light quarks for mu below scale mu. Anything above the scale mu, we consider it to be renormalized in the on-shell scheme. Now, this means that it still contributes, but it contributes to the hard cross-section. It doesn't contribute to alpha S or PDF. Okay, and then there is a scheme basically which just increments this number of active flavors as we go up in mu every time we cross the heavy quark mass threshold mu equal to MQ. We include this new active flavor as in the running of alpha S and PDF. So that's kind of a typical scheme, which is called a variable flavor number scheme, right? So it's the most common scheme, but very often people use something else. Okay, now, in fact, the same logic applies for beyond the standard model. Okay, so now imagine you have a BSM particle. Well, you ask, well, what do you do with the BSM particle? Well, you can put it in the hard cross section, but it also maybe, well, generally if it is massive, so every propagator of this kind will be suppressed by 1 over mass of the particle squared, right? So then you could say, because these terms are small, okay, I can use the on-shell renormalization for this specific particle. And now the way this works, well, an example, again, so in principle, you, at a given low energy, let's say the energy of the LHC, in principle, a quantum fluctuation can temporarily produce any heavy particle or any heavy object. And like somebody, well, like a very famous professor who gave the lecture the previous time, he said that, okay, in quantum field theory, production of any object is allowed. Okay, so now the way I think about it is, well, there is this famous book, The Hitchhiker's Guide to the Galaxy. And if you remember, well, those who read it, so there was a so-called infinite improbability drive, which can make any infinitely improbable event possible, right? And so then this infinite improbability drive will malfunction, and it created a whale in the upper atmosphere, right? And so then the whale, okay, it was completely self-conscious whale. And for a minute or two, while he was falling down, it was thinking, oh, what's happening, and couldn't figure it out. Okay, so now what quantum field theory does is essentially can produce any whale and anti-whale simultaneously, right? And so they come up into the existence, but then we don't see them at the LHC, obviously, right? So the reason we don't see them at the LHC is because we renormalize them in the on-shell scheme. So they are a part of alpha S or the running mass. But that's not the whole story, because what may also happen, okay, so first of all, these wheels will contribute to the loop corrections for electroweak parameters of the standard model, and therefore you can look for traces of these quantum whales in the so-called global electroweak feeds. They may produce some small deviations from predictions where no whales exist, right? But the second possibility is that if you have a propagator in the regular standard model process, and so you kind of have a whale that comes up temporarily from the existence, created the propagator, but the propagator will typically, for each whale, you pay the price of 1 over m squared, where m is the mass of the whale, right? But now if the whale has a mass of, let's say, 20 TeV or so, what will happen is that you will have additional so-called contact interactions that kind of appear like corrections to the standard model Lagrangian, and you can actually look for evidence of these contact interactions. So that's actually an important part of the research that is being done right now in the LHC community. So there are so-called standard model that fits in the effective field theory that improves the standard model. So it's called so-called SMEFT fits. And so they have a collection of about 100 terms like this from this contact interactions of dimension 6, 8, and so on. And so they try to fit pattern distributions together with these contact terms.
So they say, let's try to constrain PDFs together with the particle distributions. Okay. So then there is a very interesting question is, well, does this approach make sense? And why? And first of all, why do we need to feed PDFs together with these contact terms? Well, the answer is that there is a substantial freedom in the definition of the PDFs. And therefore, let's say a change in the PDF that is still allowed by the data, in some cases will look up like a contribution from this additional contact term. In fact, one of the stories that is close to the heart of CTEQ was happened in when jet production was first measured at high energy at the Tevatron in 1990s. And one of the collaborations observed that the data started exceeding theory at energies about few hundred GeV. And so that's precisely what you would get if you have some of these additional new particles that contributes a contact interaction at large ET. So then the contact interaction will go, in this case, like ET squared, the energy of the jet, divided by m squared, the mass of the particle, and times some effective constant that arises from the spinor terms. So then now, therefore, if it is squared is a order m squared, you expect seeing enhancements in theory. Now, then there was excitement for a while that, okay, so the Tevatron now sees evidence of deviations from the standard model. But then what happened was that it turns out the gluon PDF was not well-defined, even though people thought that it is well-defined. So at that time, people did not estimate uncertainties on PDFs. And so the models for the PDFs, for the gluon PDF especially, that existed at the time, they predicted the rise until the Tevatron data was put in. And so when the Tevatron data was put in, so the gluon PDF went down. Went up at large ET. And then the next generation of predictions actually went quite well through this data without any new physics. Okay, so now the message from this comparison is that actually you need to know uncertainties on particle distribution functions together with the central value. And a lot of discussion in the community is about quantifying uncertainties on PDFs, which is still a very active subject. And there are lots of discussion, and maybe in the second PDF lecture, we'll talk a little bit about it. Okay, all right, so therefore, just to review this section, so okay, so the loop graphs actually they know about physics at very small scales, very small time scales, very large energy scales. And we remove these effects from the time scale typical for perturbative graphs by incorporating these effects in the running couplings and the running masses, or we can use the on-shell scheme to do the same, right? And so the typical scale mu must be usually chosen to be of the order of the physical scale of the problem, but the coefficient is arguable. And so again, you will see different prescriptions for doing that. Okay, and so of course it's very difficult to find the evidence of new physics at the LHC if it's the typical masses of this new physics are much larger than collider energy. Okay, any questions about this? Questions? Okay. Okay, now I'll give you a few more kind of practical information that will be relevant to hadron-hadron collisions. Okay, so now one of the important processes that will be discussed in later lectures is the Drell-Yan process, right? So we talked about DAS, we did not talk yet about the Drell-Yan process. Now the kinematics of the Drell-Yan process is somewhat different from DAS because it has two hadrons in the initial state. And then there are other processes which are kind of look more similar to Drell-Yan, but they're not the same. And let me give you a couple examples. New particle production is one of them. Jet production is another one. Okay, so then when you calculate the predictions for the let's see, hadron collisions, one important quantity is called rapidity. Now, anyone is not familiar with rapidity? So how many of you have never heard about rapidity before? Okay, do I need to explain what rapidity is? Okay, so you can take a look again. So basically, okay, rapidity is instead of using let's say cross section in terms of the Bjorken X, typically will measure cross sections in terms of rapidity. Okay, and so rapidity is essentially it's if you like, it describes the boost from the proton center of mass frame to parton center of mass frame. So rapidity is basically associated with that boost transformation. Okay. So now, so the other way of obviously is that every final state particle of a final state will be associated with its net rapidity. And so then, when you do the boosts along the z direction, so rapidity is changed additively. So this is a very good important. Well, even though you have a boost, which is a rotation according to the Lorentz group, well, in fact, the rapidity transforms linearly, additively when you do the boost along the z-axis, and that's why, excuse me, it is convenient for working for hadron-hadron collisions. Now, another quantity which is related to the rapidity is called pseudo-rapidity. So what is the pseudo-rapidity? So the pseudo-rapidity is an angular variable which is related to the polar angle of the escaping particle with respect to the z-axis. And so, so it's defined according as minus log 10 theta over 2, but you can show if the final state is massless, or it has a small mass, so then the pseudo rapidity is very close to the rapidity. Okay, so therefore it's easier to measure the angle, so that's why people use pseudo rapidities in this analysis. Okay, so then I would like to flash the cross section. And by the way, in these cross sections, in these slides that I'm using, Q was replaced by M, by capital M. Okay, so don't get confused here. So, so M now in this case is the invariant mass of the final state. Okay, but I will, in other slides, you will see it is still denoted as Q. Q and M here are interchangeable. Okay, so the important thing about the process like the Drell-Yan process. And what is the Drell-Yan process? Well, the Drell-Yan process is where we scatter two hadrons and we produce a colorless final state. Okay, it can be Z, can be W, can be a lepton pair that is produced from the decay of ZOW. It can be Higgs boson. Higgs boson production is kind of like a Drell-Yan process, except it is produced in the scattering of two gluons, not of the quark and the anti-quark. But kinematically, they are all very similar. And the factorization formula is also very similar. So if you want, so typically, for example, we can plot this cross-section as a function of the rapidity of Z or another final state. Okay, and so then the expression for the factorized cross-section now includes the hard cross-section for the pairwise scattering of partons A and B multiplied by 2 PDFs. And so one PDF will depend on the momentum fraction CA. Another PDF will depend on the momentum fraction CB. Okay. Now in DS, you remember there was one momentum fraction, which at the leading order, well, that momentum fraction was simply equal to the Bjorken X, C equal to X. Okay. Now here we have two momentum fractions and we have a rapidity. But at the leading order, if you exclude all additional radiation, well, you can show that CA must be equal to XA, which is given by this formula here. So basically, when you increase the rapidity, XA increases all the way to 1. And so basically, when maximal rapidity is reached. And CB for the second particle at the leading order is equal to XB, where now rapidity enters through the exponential with the negative sign. Okay. So these are two important formulas. Now, immediately what they tell you is that actually, if you know M squared or Q squared for the final state, you know the rapidity, you can immediately estimate what the typical momentum fractions for the parton A and parton B are from this formula. So these are very useful formulas to remember. Okay. Okay. So then if we look at the formula, continue looking at this formula again, this formula contains the factorized expression for the leading power term, but there are also some power suppressed corrections that go like small m or small lambda QCD or lambda QCD divided by the capital M or Q, right? Okay, so therefore, again, this formula works better at high Q because first of all, alpha S is small, And well, you get a better convergence for the cross prediction. Is to get an accuracy of a few percent, you need to go to N3 law nowadays. So basically, you need to go to very high in alpha S. But also, if you go to high Q, you suppress the power corrections. And a very important question for experiments like fixed target experiments at the Tevatron or Sequest experiment will be another good example, or Compass experiment is this power suppressed corrections can no longer be negligible, and we have to be very careful. Okay, now the other thing is that here this formula is shown for the cross section that is integrated over the whole transverse momentum. Okay, so it's therefore you apply the one scale factorization. So I'll show you in a little bit later what happens when QT is much smaller than m squared or q squared. Okay. Okay, now that's the formula. Okay, but then you ask, well, again, just like with DAS, is this actually formula actually proved or not? Okay, so does it hold to all orders? And so the answer is yes. But if you would like to look at the proof, it's very complicated. It's much more complicated than in deep inelastic scattering. And the main reason is the following. So it's related to the fact that we have shock waves. So when you have two, so now you have two hadrons, and you have two shock waves passing through each other. So now this shock wave generally will have different phases. And so when they pass through each other, you can create a splash in the field. That is basically, it's a splash field. It's a very, very powerful splash that goes through the whole area that is occupied by the hidden elements. So the splash is called the Glauber mode. Glauber mode, derived from the shock wave. And so these Glauber modes, they really mess up the proofs for the factorization for hidden collisions. Okay, only recently we have very nice developments by SCAT theoreticians who show how to handle these Glauber modes properly, but they make life much more difficult compared to deep inelastic scattering. Okay, and furthermore, something else I would like to mention. So what also helps in this case is that this is the single inclusive production of a colorless final state. So this fact again simplifies proof of factorization, because if the state were to carry color, you could have additional interactions between initial state radiation and the final state radiation, and so then the whole formalism of proving factorization becomes intractable. So you have many technical complications. That's why, for example, for jets or for in general color particle production in hadron collisions, you do not have the systematic proof of factorization, even though people believe that it works. Okay. So now heavy particle production. Well, you can in hadron collisions you can also produce heavy particles. Well, here is an example. You can produce BB bar pairs, right? And so then you will write the diagram like this. Okay. So then you ask, what does heavy mean in this case? Well, heavy here means that the mass of the particle is larger than 1 GeV. Okay, but how heavy it is, well, it kind of depends on the Q scale, or the square root of S value, right? If you work at the fixed target experiment, so this heavy particle, let's say the bottom quark, well, you barely produce it. And you can simply include these heavy quarks in the hard scattering cross section. You do not need to include this, in fact, in the running of alpha S or running of the PDFs. So therefore, you will work in so-called four active flavor scheme. If you go to the LHC, so there the typical scales are much larger than bottom mass. You will use the 5 flavor scheme. Now the LHC actually probes the whole range of energies. So then there is this very interesting question. You may want to use 4 flavor scheme in one part of the phase space and 5 flavors scheme in the other part of the phase space. So then there must be a prescription how to match the 4 flavor calculation with the 5 flavor calculation. Okay, so we can talk about it at recitation. All right, so what about jets? So jets is another process that you studied in hadron collisions. Well, now the jets now have the color in the final state, and you have massless quarks. Massless quarks radiate much better than massive ones. Okay, so therefore, well, with the heavy quarks, actually, you do not see such a well-developed jet as for light quarks. So the light quarks really shower like crazy. Okay, and so then you also need to define what you mean by the jet. So remember, we said, okay, the first approximation, well, if you see some collimated flow of particles, well, you say that's a jet. But you have some ambiguity what you mean by the jet. For example, what is the radius of the jet? Okay, so what kind of particles you include in the jet? Do you include the electromagnetic calorimeter and hadronic calorimeter signal? Do you include the tracks? And this definition must be infrared safe. Okay, so what this means is that now if you have a soft particle, so your distribution of the jet should not change whether you add an additional soft particle to the jet or not. Okay, so that's now it becomes very tricky because, okay, so this formula of infrared safety that I discussed yesterday, now I strongly encourage you to review it. So actually it's quite relevant for so-called jet algorithms that define what jets mean. Of course, once we identify jets, then we can say most of the energy of the jets comes from the its apparent parton, and so we can do a calculation in the fixed order perturbation theory. But to define a jet, well, you need to have an infrared safe algorithm. Okay, so then there are various kinds of algorithms. Okay, now again, so all algorithms will kind of resort to the same big idea is that jet is a spray of hadrons. But the definition can vary, and so the definition must be infrared safe. Okay, so it can be based on the cones, it can be based on transverse momentum of the particles. You can somehow combine particles into this jet. Okay, now the LHC uses a particular kind of algorithm which is called the anti-KT jet algorithm. And so this anti-KT jet algorithm is, well, it actually performs much better than the other types of algorithms. Okay, so here is an example from this very famous paper that introduced this anti-KT jet algorithm, which shows how various particles are clustered into jets depending on the type of the algorithm. And so what is shown here on the, okay, so it's essentially a plane that expands the solid angle into a in the two-dimensional rectangle. You have a plot of rapidity of the jet on the one axis, and you have the plot of the azimuthal angle on the other axis. And so here you have on the vertical axis you have PT of the jet, PT of each particle. So then each particle will create a little, if you like, bar in this plot. So this is so-called Lego plot. So basically, each particle will deposit a little Lego bar onto this plot, but then somehow you need to combine these Legos into what you call a jet. So then you can run an algorithm which does this combination, and you can see that some algorithms that are traditional ones, the results in the jets that are very jagged, very weirdly shaped. Okay. But then this new anti-KT jet algorithm, first of all, it captures all particles. It assigns all particles to the jets. But also these jets have a very nice, almost like circular shapes. And that's sort of the feature of this anti-KT jet algorithm. And that's why people like using it. It's a very stable, infrared safe, but also very intuitive algorithm. Okay. Now, yeah.
Here you turned on the full standard one to go to system. Because before we had just QCD, right? When we were starting factorization.
Right.
Okay, so these two processes are completely different algorithms.
Yeah, so then, yes, the jets generally will include the leptons and photons and whatever else. And of course, the contribution is relatively small because the electromagnetic processes, they are kind of rare. So they will not change the big picture of jet distribution. Right, so but yes, we do include those, and parton showers include those additional showering contributions. Okay, so there is this anti-KT jet algorithm, and so I probably will not discuss it now, but if there is interest, we can discuss it during the recitation, how it works, and I encourage you to review it. Okay, and so here is an example how the anti-KT jet algorithm works. What essentially it does, here we have pseudo rapidity, not rapidity, showing, let's say, 5 individual particles. And what you start doing then is that basically you have 2 particles with low KT here, and two particles with high PT here and one particle with PT here, right? So then the typical question is, okay, so first of all, you need to define what the jets are. For example, you need to say, is this particle is a jet or not? Is it a jet or not? Right, but then you need to combine the particles that are close in the direction depending on their PTs, right? And so in this case, we have three jets that are formed. But then you can ask it, like, for example, you can play the game, you say, okay, now imagine I put a soft particle here. So then now you can have two possibilities. You can have a possibility that this particle, soft particle, is attributed to one of the jets. And actually this jet now is located not here, but it will be located somewhere here. It will carry different energy, right? But the nice feature about this anti-KT jet algorithm that this particle will not be assigned to any jet. Okay, so that's very important. So that's that's why this algorithm is liked. It is infrared safe. It is not sensitive to this kind of perturbations. Okay. Okay, so then to review this, right? So so in general, we apply factorization and it works reasonably well. Perturbation theory converges very well, but you need to have typically high momentum scale in this process, right? Like we produce very heavy particles, right? Or you can produce particles with high transverse momentum. Then the high transverse momentum will be another hard scale, right? And you need to define the predictions in the infrared safe way, right? Or in the way that can be factorized. So you have a hard cross section. Hard cross section must always be infrared safe, right? But maybe when you calculate the full cross section, you need to combine this hard infrared safe hard cross section with the non-perturbative functions, right? And then the typical factorization formula for hadron-hadron collision looks like this. Okay, so you want to remember that. Okay, so let's see. Any questions before we move on to large logarithms? So far, so good. All right, so the last thing I would like to tell you a little bit about this issue about summation of large logarithms. Okay, and it emerges when in addition to the hard scale Q, we have some other scale, which can be much smaller or much larger than Q. And you cannot just factorize it into the PDF, right? So now a typical example will be, okay, so now again, so first of all, let me remind you why this is the issue. Well, the issue is that for an infrared safe process with one hard scale, the theory is simple, but if there are two hard scales, we need to do something else, right? So for example, we take this Brilliant process, and now we measure the transverse momentum of the particle, right? In addition to the rapidity, well, if Qt squared is of order Q squared, we produce a high PTZ boson. Well, you just say Qt squared and Q squared is just one hard scale. I don't draw any distinction. I apply the standard one scale factorization formula, just like here. If I integrate Qt out, well, there is no dependence on Qt implicitly, right? So you still have one hard scale Q. So you apply one scale factorization. Now you say, I'll look at the Z bosons that have very small transverse momentum. Well, then, okay, now you have two possibilities. Qt squared is much smaller than Q squared, but it is still much larger than one GV squared, right? So then you will see large logarithms. Well, basically, they're kind of unavoidable. So you select whatever mu r and mu f you select. You will have either large log Q squared over mu squared or large Q squared over Qt squared, or Qt squared over mu squared. You cannot avoid the log, right? Now, if Qt squared becomes much less than 1 GV squared, you have an additional problem now. Okay, so there will be contribution where alpha S runs to very low scales below 1 GV. Okay, so therefore there is an additional non-perturbative contribution. Well, in this case, it will be associated with so-called non-perturbative intrinsic transverse motion of particles inside the incoming hadrons, right? So then there are additional types of factorization. And the very well-known one is the transverse momentum dependent factorization that shows how to properly organize factorized cross-section in a way so that you sum these large logs like to all orders. So just like in the PDF, we sum large logs of mu squared f squared over m mass of the quark squared. Here we'll have additional terms in the cross-section, which will sum also other logs like log Qt squared over Q squared, okay? All right, now it works not just in Brilliant process. In fact, it also works in E plus and minus heat reproduction, and it works in CDs. And remember why this is the case? Well, because if we go to the first lecture, I mentioned to you these three important processes, right, which are related by crossing. So Brilliant, E plus and minus heat reproduction, and CDs. In all of these processes, you can introduce the scale Q, you can introduce scale QT. So therefore, in E plus and E minus heat reproduction, they can be also observables that effectively depend on QT over Q. They may be phrased as the processes that depend on some angles. So when the angle becomes either close to 0 or close to pi, so you will have a large contribution. But it's the same idea. So there are these basically two scale logarithms that are important. For example, so in the first lecture, I showed you the variable called the observable called the thrust, right? And so it kind of measures the sphericity of the events, right? And so basically the thrust equal to 1 corresponds to the jets that are exactly back to back, or particles back to back. And if you have t larger than 1/2, you have essentially kind of an isotropic distribution, right? So then now, if we look at the limit when t equal to 1, so this is the leading order configuration. Remember, so you produce two jets back to back, right? So if t is slightly larger, so slightly different from 1, so there is this angle theta, which is our order qt over q. So this means that there is a soft radiation that recoils against these two jets. Okay, so therefore, your fixed order thrust distribution will contain something, let's say not singular, but let's say problematic behavior. It will contain log 1 minus t, or maybe it will contain 1 over 1 minus t, right? And so that's actually what we saw in the fixed order calculation. We looked at this 2 to 3 process, the first order correction to the thrust calculation, and I wrote for you the formula, which looked like this. So the formula behaves very well when t is far from 0 from 1. But if t goes to 1 to the jet to the back-to-back configuration, well, you have 1 over 1 minus t here and here, and you have a log of 1 minus t here, right? So you start picking up these bad behaviors, okay? So in fact, if you set t exactly equal to 1 for this diagram, so it will blow up, it will have a soft singularity, but at the same time, you also have another term, a diagram, which will have the virtual correction. And so the virtual correction will have a soft singularity of exactly the same magnitude and an opposite sign. Okay, so the soft singularity in the virtual will cancel the soft singularity in the real diagram. You will not have the soft singularity anymore, but you will still have a problem. You will still have a large log in the thrust distribution. So then you will apply a summation to sum all these residual logs to all orders. Okay, and so what you will get is a distribution that looks something like this. So this is a figure from a very famous calculation of resummation for the thrust distribution, which was done in 1990s. Okay, so here we plot 1 minus t, right? So the back-to-back configuration is right here. Okay, and so here we plot a piece that corresponds to this 2 to 3 that diagram with 1 gluon emission. So then if the gluon is hard, we see it over here. And so then the fixed order result behaves very well. It also agrees with a variety of measurements very well. Now, if you go to very small 1 minus t, so the fixed order correction, I think in this case, it behaves as this red curve. So the red curve kind of blows up. So it behaves very badly. But then we can properly cancel soft singularities. There are no collinear singularities in this case. And then we can resum the remaining logs to all orders. And so then we'll get this curve, which is called a next to leading log curve. So it means that resummation was done at the next to leading log accuracy. And so there is a way to count these logs. Okay, so actually this red curve is not the fixed order. So the fixed order will simply blow up, but the pure resum curve will be the red curve. And as you see, the red curve, it kind of follows the data, but it is not describing the data properly. Well, why is that? Because the reason is that this resummation is sensitive to additional kinds of non-perturbative contributions, so power corrections. And I mentioned to you there is this intrinsic motion of the partons inside the hadrons. And so that's kind of the most important contribution here. Now, these power suppressed contributions can be included, often is included in these result calculations. And so then, in fact, is actually quite important in this case, right? So it brings the red curve close to the black curve, which is the full resummation calculation. And you see the black curve agrees with the data very well, while the red curve agrees with the data only at well, t above 0.1 or so, right? So the resummation work without no perturbative correction works reasonably well. Well, in somewhat what we call a matching region, but it will okay, did not describe the theory data well at very small values of 1 minus t. Yes.
How are these power correction? How are the power correction?
So the power correction basically well, you can try to calculate it, and so there are ways to try to for example, lattice QCD calculates so-called Collins-Soper kernel, and so that Collins-Soper kernel includes a non-perturbative part, right? So you can try to calculate it, but the other way you say, okay, so this correction now remember in the fixed order calculation, we had correction of order some kind of non-perturbative scale divided by q, right? So here, okay, by the same logic, you must have a correction that will be okay. So now, yeah, so it will be something like probably okay. So I'll try to write it down. Basically, you can do an order of magnitude estimate here, right? So it will be a power suppressed correction in T. And do we have a power suppressed terms here? Yeah, we don't have those, but you can introduce basically an additional term that is of order probably 1 minus t to some power squared, something like this. And yeah, so basically you can guess the form of this power correction based on the basic properties of the resummation cross section. For T, I don't remember how exactly it looks like, but for example, for the Drell-Yan, where you have this contribution, so you will have a correction of order lambda QCD squared over QT squared. So that will be the correction. And so then there is an unknown coefficient in front of it, and basically you put this correction in, and you try to fit it together, basically to fit it to the data. So that's how people find it.
Okay, so basically they are reabsorbed by UPDFs, like how
so there will be okay, so they will not be reabsorbed in the PDF. So okay, so this formula will depend on the regular PDFs, but in addition, there will be an additional factor which is called the soft factor. And so the soft factor will contain the perturbative part, which contains this perturbative logs that are summed to orders. And then there is an additional contribution that comes from this non-perturbative region where QT squared is a order lambda QCD squared. And so then the soft factor will also include that additional term, which is non-perturbative. And so if you like, again, so I hope there will be a lecture about this, but if not, we can get together and I will work out the formula for a summation for you to show how it works during the recitation. Yeah. All right, so I think that's all that I wanted to tell you, and just to summarize this this resummation part, right? So again, the point here is the following: that we must have at least one energy scale above 1 GeV, or to have a small perturbative coupling, right, in the applied perturbation theory. But then, okay, so when all scales are of the same order, we can just apply the collinear factorization like there. When some scales are much smaller or much larger than our hard scale, chosen hard scale, well, we may need a different type of factorization, which is called resummation, right? And so then there are various kinds of resummation formalisms. I described one of them. Yeah, well, it's called TMT resummation, but there are other resummations as well. And so again, we can talk about different kinds of resummations in due time. Okay, and I think with this, I want to conclude this introductory part and just to thank my colleagues who put this deck of slides over many years. So it's not just me for all of them, there is a lot of input from
our many CTEQ members, and again, we can have a few more questions. Anything else we need to discuss to prepare you for the remaining lectures?